Hello everyone, welcome to Happy Chemistry. Let's begin today's lesson. Significant figures. Significant figures is a very important topic in any field of science. We will cover all the aspects related to significant figures in this episode of Happy Chemistry. First of all, what do we mean by significant figures? The minimum number of digits needed to write a given measurement without the loss of precision is called number of significant figures. Let's look at an example. Let's assume this is a density calculation. 85.72 grams in 6.05 milliliters. What is the density in grams per milliliter? To get the answer, we have to divide 85.72 grams by 6.05 milliliters. When we perform the calculation using a calculator, we will get an answer with many decimal points. For this division, we will get 14.168595 and decimal places even beyond that if I did not stop writing them. So, in what form you are going to present your answer? Most importantly, what is the correct form of the answer? We have to present the answer without underestimating or overestimating the number of digits. To do that, we need to understand the concept of significant figures. The first step of understanding the concept of significant figures is to know how to accurately count them. There are 6 rules that you need to follow. I will go through them one by one. I will also give a simple example to understand each rule. The first rule: start counting the numbers from left to right. When you decide the desired number of significant figures for your answer, start counting from left. For example, we have a number 14.168595. Based on the calculation, let's assume the desired number of significant figures is 3. Then start counting from left. 1, 2, 3. Therefore, only 14.1 is significant, and rest of the numbers are not significant. However, in this case, 14.1 will not be the final answer. We will talk about that kind of examples in my next slide. The second rule. The second rule is all non-zero digits anywhere in the number are significant. In the example, we have a number with all non-zero digits. Start from left. 1, 2. Therefore, number of significant figures are 2. The rules 3 to 6 are about counting zeros when they are at beginning, between, and at the end of numbers. Let's see them one by one. Rule number 3. Zeros at the beginning of a number are not significant. Zeros at the beginning of a number are not significant. Let's see the example. Start counting from left. Not significant, not significant, 1, 2. Therefore, number of significant figures are 2 in this number. Rule number 4. Zeros in between the non-zero digits are significant. Zeros in between the non-zero digits are significant. Look at the example. The 0 is in between non-zero digits. Therefore, it is significant. Start counting from left. 1, 2, 3. 3 significant figures in the given example. Rule number 5. Zeros at the end of a number are significant if it is a decimal number. Zeros at the end of a number are significant if it is a decimal number. Let's see the example. The 0 is at the end, therefore significant. Start counting from left. 1, 2. 2 significant figures in the given example. Rule number 6. Rule number 6 is sort of related to rule number 5. In rule number 5, we said the zeros at the end are significant only if it is a decimal number. There are 2 parts for the rule number 6. The first part of rule number 6 is the zeros at the end are not significant if it is not a decimal number. Look at the example. 1250. This is not a decimal number. Therefore, the 0 at the end is not significant. Start counting from left. 1, 2, 3. 3 significant figures in the given number. There's a second part of the rule number 6. That is, the numbers with zeros at the end can be written in scientific notation to get the desired number of significant figures. I repeat, the numbers with zeros at the end can be written in scientific notation to get the desired number of significant figures. We will take the same example. 1250. When written in scientific notation, it is 1.25 into 10 to the power 3. Now, this is a decimal number. Start counting from left. 1, 2, 3. 3 significant figures. If we write the same number as 1.250 into 10 to the power 3, it is now a decimal number and the end 0 becomes significant. Start counting from the left. 1, 2, 3, 4. 4 significant figures. If you write it as 1.2500 into 10 to the power 3, both zeros at the end become significant. Start counting from left. 1, 2, 3, 4, 5. 5 significant figures in this number. These are the 6 rules of counting significant figures. It is a very important aspect of the significant figures concept. Now let's see how to use the significant figures in calculations. There are 3 types of calculations: addition and subtraction, multiplication and division, logarithm and antilogarithm. However, before performing any of these arithmetic functions, there is another important aspect that needed to be learned. It is important in all types of arithmetic functions to decide the final accurate answer. This is rounding off. So now we will see what are the rules for rounding off. For this, first you need to decide how many significant figures are desired. And then the general rule is you have to look all the digits beyond the desired place. I repeat, look all the digits beyond the desired place. According to how these rest of the digits look like, there are 3 different rules. We will talk about these 3 rules. Each rule is given 2 examples, assuming the desired number of significant figures is 3. The first rule is, if the digits beyond the desired place is above halfway to the next higher digit, round up the desired digit to the next higher digit. If the digits beyond the desired place is above halfway to the next higher digit, round up the desired digit to the next higher digit. Let's see the example. As I said, it is assumed the desired number of significant figures is 3. The digit at the desired place is indicated in blue. All digits beyond the desired place is indicated in red. The desired digit after rounding off is indicated in green. The first example is 1.4283. The digits beyond the desired place is 83, which is above halfway. Therefore, 2 is rounded up to the next higher digit, and the final answer would be 1.43. In the second example, the number is 1.4251. The digits beyond the desired place is 51, which is above halfway. Therefore, 2 is rounded up to 3, and the answer would be 1.43. The second rule is, if the digits beyond the desired place is below halfway to the next higher digit, round down the desired digit. I repeat, if the digits beyond the desired place is below halfway to the next higher digit, round down the desired digit. The first example is 1.4233. The desired digit is 2, and the digits beyond the desired place is 33, which is below halfway to the next higher digit. Therefore, round down and keep it as it is. The final answer would be 1.42. The second example is 1.4249. The digits beyond the desired place is 49 and below halfway. Therefore, round down the desired digit and keep it as it is. The final answer would be 1.42. The third rule is, if the digits beyond the desired place is exactly halfway to the next higher digit, then round up or round down the desired digit appropriately to the next higher even digit. I repeat, if the digits beyond the desired place is exactly halfway to the next higher digit, then round up or round down the desired digit appropriately to the next higher even digit. Let's see the example. The first example is 1.4150. The digits beyond the desired digit is 50. That is exactly halfway to the next higher digit. Therefore, round up the desired digit to the next higher even digit. the final answer would be 1.42. The second example is 1.4250. The digits beyond the desired place is 50, that is exactly halfway through. However, the desired digit is already an even number. Therefore, has to round it down. The final answer would be 1.42. To summarize the rules again, the first rule is if the digits beyond the desired place is above halfway to the next higher digit, round up the desired digit to the next higher digit. The second rule is if the digits beyond the desired place is below halfway to the next higher digit, round down the desired digit. The third rule is if the digits beyond the desired place is exactly halfway to the next higher digit, then round up or round down the desired digit appropriately to the next higher even digit. Now that we know how to round off, we will now see significant figures in calculations. First, we will look at addition and subtraction. There are two rules. The first rule in addition and subtraction is the answer should be kept the same number of decimal places as the measurement with fewest decimal places. It is important to note that here we are looking at the minimum number of decimal places and not the significant figures. Accordingly, we will get the right number of significant figures for the final answer. The desired digit, according to the number of decimal places, is indicated in blue in the examples. We will look at an example for addition. 92.5 is added to 42.154. The answer is 134.654. 92.5 has one decimal place. 42.154 has 3 decimal places. Therefore, the answer should only have one decimal place. Therefore, in 134.654, the desired digit is 6. The rounding off rules apply here and the desired digit is rounded up to 7. The final answer is 134.7. We will count the significant figures. 92.5 has 3 significant figures and 42.154 has 5 significant figures. After addition, before rounding up, 134.654 has 6 significant figures. With the minimal number of decimal places, final answer is 134.6 has 4 significant figures. Now we will look at the example for subtraction. 42.154 is subtracted from 92.5. The answer is 50.346. Similar to earlier example, 92.5 has one decimal place and 42.154 has 3 decimal places. Therefore, the answer should have only one decimal place. In 50.346, the desired digit is 3. The rounding off rules apply here. The desired digit is round down and the final answer is 50.3. Let's look at the number of significant figures. 92.5 has 3 significant figures. 42.154 has 5 significant figures. 50.346 has 5 significant figures. The final answer with one decimal place has 3 significant figures. The second rule in addition and subtraction is, if the numbers are in scientific notation, they should be written in the same exponent before performing the mathematical function. The final answer should be kept the same number of decimal places as the measurement with fewest decimal places. Now we will look at an example for addition. 1.3 into 10 to the power 5 is added to 2.56 into 10 to the power 4. You can see these two numbers have two different exponents, 10 to the power 5 and 10 to the power 4. First, we will convert them to a single exponent. Here, I have converted 2.56 into 10 to the power 4 into 0.256 into 10 to the power 5. Now both numbers have the same exponent. Now carry out the addition as a normal number. Exponents will not add together. It is same for the answer. The answer is 1.556 into 10 to the power 5. 1.3 into 10 to the power 5 has one decimal place. 0.256 into 10 to the power 5 has 3 decimal places. Therefore, answer should have only one decimal place. 1.556 into 10 to the power 5 has 3 decimal places. Therefore, the desired digit would be 5 in the first decimal place. After rounding up, the answer is 1.6 into 10 to the power 5. Here, 1.3 into 10 to the power 5 has 2 significant figures. 0.256 into 10 to the power 5 has 3 significant figures. 1.556 into 10 to the power 5 has 4 significant figures. After keeping the right number of decimal places, 1.6 into 10 to the power 5 has 2 significant figures. Now we will look at an example for subtraction. 2.56 into 10 to the power 4 is subtracted from 1.3 into 10 to the power 5. As earlier, they have different exponents. Therefore, 2.56 into 10 to the power 4 is converted to 0.256 into 10 to the power 5 to get the same exponent. Now perform the subtraction. The exponents are not subtracted. The answer is 1.044 into 10 to the power 5. 1.3 into 10 to the power 5 has one decimal place. 0.256 into 10 to the power 4 has 3 decimal places. Therefore, the answer should be kept in one decimal place. 1.044 into 10 to the power 5 has 3 decimal places. Therefore, the desired digit is 0. After rounding down, the answer is 1.0 into 10 to the power 5. Now let's look at the significant figures. 1.3 into 10 to the power 5 has two significant figures. 0.256 into 10 to the power 5 has three significant figures. 1.044 into 10 to the power 5 has four significant figures. After keeping the right number of decimal places, the answer is 1.0 into 10 to the power 5 has two significant figures. So these are the two rules for addition and subtraction. First, the answer should be kept the same number of decimal places as the measurement with fewest number of decimal places. Second, if the numbers are written in scientific notation, all numbers should be written in the same exponent before adding or subtracting. Now we will look at multiplication and division. There are two rules. The first rule is the answer should be kept the same number of significant figures as the measurement with fewest number of significant figures. It is important to note that here we are looking at the minimum number of significant figures. The desired digit according to the number of significant figures is indicated in blue in the examples. We will now look at an example for multiplication. 35.35 is multiplied by 1.72. The answer is 60.802. 35.35 has four significant figures. 1.72 has three significant figures. Therefore, the answer should have three significant figures. 60.802 has five significant figures. To have three significant figures, the desired digit would be 8. After rounding down, the answer would be 60.8. Now let's look at an example for division. 35.35 is divided by 1.72. The answer is 20.55232558 or more decimal places. 35.35 has four significant figures. 1.72 has three significant figures. Therefore, the answer should have three significant figures. However, 20.55232558 has 10 significant figures. To have the correct number of significant figures, the desired number is 5 indicated in blue. After rounding up, the answer is 20.6. Now let's look at the second rule. The second rule is the numbers in the scientific notation can use as it is in multiplication and division. And the answer should have the same number of significant figures as the measurement with fewest number of significant figures. Let's look at an example for the multiplication. 35.35 into 10 to the power minus 5 is multiplied by 1.72 into 10 to the power minus 2. Here we can separately multiply the number and the exponent. 35.35 is multiplied by 1.72 is 60.802. 10 to the power minus 5 multiplied by 10 to the power minus 3 is 10 to the power minus 7. Therefore, the answer is 60.802 into 10 to the power minus 7. This can be written in a better representation as 6.0802 into 10 to the power minus 6. 35.35 into 10 to the power minus 5 has 4 significant figures. 1.72 into 10 to the power minus 2 has 3 significant figures. Therefore, the answer should have 3 significant figures. To have the correct number of significant figures, the desired digit in 6.0802 into 10 to the power minus 6 is 8. After rounding down, the final answer with 3 significant figures is 6.08 into 10 to the power minus 6. Let's now see an example for the division. 35.35 into 10 to the power minus 5 is divided by 1.72 into 10 to the power minus 2. Here also separately divide the number and the exponent. 35.35 divided by 1.72 is 20.55232558 and beyond. 10 to the power minus 5 divided by 10 to the power minus 2 is 10 to the power minus 3. The answer is 20.55232558 into 10 to the power minus 3. In a better representation, this can be written as 2.055232558 into 10 to the power minus 2. 35.35 into 10 to the power minus 5 has 4 significant figures. 1.72 into 10 to the power minus 2 has 3 significant figures. Therefore, the answer should have 3 significant figures. To have the correct number of significant figures, the desired digit is 5, indicated in blue. After rounding up, the final answer with 3 significant figures is 2.06 into 10 to the power minus 2. So these are the 2 rules for multiplication and division. First, the answer should be kept the same number of significant figures as the measurement with fewest number of significant figures. Second, if the numbers are written in scientific notation, they can be used as it is even if they don't have the same exponent. Multiplication and division can be performed on the numbers and the exponent separately and work out the final answer. Now let's see rules for logarithm and antilogarithm. First, we will see the definitions for logarithm and antilogarithm. If x equals to 10 to the power y, y is the base 10 logarithm of x. That means log x equals to y. If we consider this the other way round, x is the antilogarithm of y. That means antilog y equals to x. And there's important terminology we should know. If we take a log of a number, for example, let's say 522, the logarithm is 2.717670503 and beyond. we can see there is an integer part and a decimal part. The integer part is called the character, and the decimal part is called the mantissa. These terminology are important when we discuss the rules. We will first look at the rule for logarithm. The rule is mantissa should have the same number of significant figures as the number. I repeat, the mantissa should have the same number of significant figures as the number. Let's look at an example. Let's take log of 522. Log of 522 is 2.7176705030 or beyond. 522 has 3 significant figures. Therefore, the mantissa should have only 3 significant figures. It is important to note that we are looking at the significant figures of mantissa. Therefore, to have the correct number of significant figures, the desired digit is 7, indicated in blue. After rounding up, the correct answer is 2.718. We will now look at the rule for antilogarithm. The rule is the number should have the same number of significant figures as in the mantissa. I repeat, the number should have the same number of significant figures as in the mantissa. Let's look at an example for antilogarithm. Let's take antilogarithm of 2.5123. Antilog of 2.5123 is 325.3119373 and beyond. The mantissa of 2.5123 has 4 significant figures. Therefore, the answer or the number should have 4 significant figures. To have the correct number of significant figures, the desired digit is 3, indicated in blue. After rounding down, the answer with 4 significant figures is 325.3. So these are the 2 rules for logarithm and antilogarithm. In logarithm, the mantissa should have the same number of significant figures as in the number. In antilogarithm, the number should have the same number of significant figures as in mantissa. That concludes today's lesson. In summary, we talked about significant figures, rules for counting significant figures, and significant figures in calculations. Under calculations, we covered rules for rounding off, rules for addition and subtraction, rules for multiplication and division, and rules for logarithm and antilogarithm. That covers the concept of significant figures. That's the end of today's episode. Hope you liked the video. Give it a big thumbs up. Leave your comments and questions down below. Subscribe to my channel. Turn on the notifications to be notified as soon as a new video is uploaded. Don't forget to follow me on Facebook and Twitter. Stay tuned. See you in my next episode. Until then, happy chemistry. Bye bye.